Howdy folks, I'd like to share you a subject which I a long time ago also treated with you, and I revisited for myself the whole subject, and I did some nice calculations, and I'd like to show you these calculations. I got them on my computer, so I will turn the camera to my computer, and I hope the resolution of my camera, which is a simple Nokia camera, but okay, is enough to show you all the details you need to see. Okay, one moment please. This is the computer. This is an Excel sheet, and I will enlarge, zoom into the whole thing so you can see the numbers better. Okay. I hope this is clearly visible. And if not, then I will zoom in some more. I mean, that's not the problem. Here. At least now it should be visible. Okay. Well, as I already told in the past, at least, that there you have the Earth and Moon system, and the Earth and Moon system, they are attracted to each other, just like this. You have an Earth, you got a Moon, and in between acts upon a force. Of course, the Moon is spinning around the Earth, the circle, part of a circle, and the Earth is also making a little roundabout, but not so much as the Moon, of course. And they are attracting each other. But this is a very big force, and the force I have calculated over here. And this is the Earth-Moon distance. I will zoom in a little more so you can see the numbers. It's about 384 and 400 meters. This is in meters, by the way, if I'm correct. Yeah, this is in meters. And the force is pretty big. It's, as you can see, it's about 2 times 10 to the power of 20. Now, you can calculate also, here, you can see it. Suppose that the Moon is displacing itself, like here, that it's displacing itself 1 centimeter. Suppose that is 1 centimeter. Well, on the paper it actually is, but suppose that happens to the Moon, 1 centimeter. That means that you have a force, the gravitational force, is acting upon the Moon-Earth system, and the gravitational force is doing work over that 1 centimeter. Now, so you can calculate the amount of energy that is involved in that, and that is the force, at this one, approximately 2 times 2 to 10 to the 20th, times the displacement of 1 centimeter. And 1 centimeter is 1/100th of a meter, and since all units are in like meter and kilograms and seconds and so on, you have to multiply this amount times 1/100th, or 0.01. So you end up with approximately 2 times 10 to the power of 18. That's the work per centimeter. But we know that's measured that the displacement is not 1 centimeter but 3.82, plus or minus 0.007 centimeter. That is what's known. This is measured. That's what we know. That's a fact. Well, what I here did in this column, I divided the work per centimeter by itself and related every further on work done related to this amount of work. So in our present situation, which happen to be at t is 0 years. All the amount of time is I do per year. Now, so I relate this amount of work to in this case to itself, and this amount of work I will relate to this one, and this. So this is actually basically 1. And I will see the increase in work per centimeter displacement. I will put it over here, but that's only per centimeter. Now, the real displacement is not 1 centimeter. The real displacement in our present day situation, which is real, is 3.82 centimeters. So the actual amount of energy is this one, which is simply the displacement times the displacement per, or the energy per centimeter displacement. Okay. That means that you have an energy loss, an annual energy loss of this amount of energy, 7.6 times 10 to the power of 18 joules. Yeah. And I think this is the number of watts. It depends on how many seconds per year you have. And in this case, I calculated the power of the watts, and that is this one, 2.4 approximately, 2 times 10 to the power of 11. Okay. Well, what I also did is, in the beginning, I assumed that we calculate the differences in portions of 10,000 years. That's what I did here, 10,000 years. So that means that I will do 10,000 times this displacement. I assume that this is constant for 10,000 years, which is most probably not true, but okay, let's assume you have to start somewhere. So after 10,000 years, which is seen here, increase some more, you have the starting point minus the displacement here, divided by 100, because you have to do it in meters, times the number of years, which is this, 10,000, and then start subtracting that from the original, the starting point where you started. So then you are left with this number of meters, slightly less. It's not much, but okay, it's less. So for 10,000 years, this is the result. Then again, you calculate the force, which is a gravitational force, between the two, between the moon and the moon and the Earth. Well, this is the gravitational constant, the mass of the Earth and the mass of the moon. In this case, you have to take my word for it for a moment, because that's written somewhere else in the sheet, in the Excel sheet. But I calculated. You can calculate. If you don't believe me, you can calculate. Divided by the square of the distance. That's the force by that. Okay, then you can again calculate the work done per centimeter displacement. Suppose that you displace it again a centimeter, 1 centimeter. You can calculate it, the energy done of the work done by a 1 centimeter displacement. Well, you see that if you relate it to the original, to this amount of work, then it's increased a little, maybe very little, but okay, it's not much. But okay, you have to start somewhere. But then again, you have to take that same multiplication factor to the distance that goes along with it. That's actually the same one. Here F106. Can also do it like this. 106. And do that way. It's the same. Okay. 106. That's the same. Doesn't matter where you get it. I get the same number. So you have to multiply the amount, the energy, the work per centimeters times the number times the original displacement, because the amount of energy that is released translates into a displacement. And because the energy, if you have the Moon-Earth system, then gravitational pull and the tidal force will make sure that radiation, that the energy is released in like heat, but also in displacement of rocks and friction and stuff like that. So the gravitational energy is being transferred in all kinds of other forms of energy, mostly heat and displacement of water, but also displacement of rocks. And you never see that energy again. So the energy is released in heat, and you will never be able to put it back to get the moon closer. So that the energy is lost, mainly in heat. Okay, but that means that you have a slightly increase in the displacement, as you can see here. That this was the original displacement, 3.82 centimeters to start with. This is what we measured, but the increase will, the increase in distance will slowly increase itself. If you calculate back, I mean, what we are doing is calculating back into time. So we're going back into time to see what happens. Well, that also gives a slightly higher total energy and so on. We go back to the second 10,000 years, and the same thing happens. But now you have to, of course, subtract these two, because it's the next 10,000 years, and you have to calculate the difference between these two. So again, but then again, we use this increased amount of displacement. It's a slightly increased. So we use this number instead of this one, because the displacement increased, so we have to calculate with the new found displacement. That's what I did. And subtract that from the previous amount of the previous position of the moon, which is slightly closer to the Earth, because we're calculating back in time. That goes along with a slightly higher gravitational pull. And we can repeat this this calculation over and over and over again. So this is the force, this is again the energy per centimeter, this is increased relatively to where we started from, and based on that we calculate an even higher, an even higher displacement. Well, then we go back, and here again you do the whole process over and over and over and over and over and over again with increased numbers of years. Well, I did that. I calculated a lot of years, and also in some places I made the steps bigger, and so on. So what you can see here is that the force increases, the distance between the Earth and the Moon is gradually reducing, so the Moon gets closer if you calculate more back in time, and the force is increasing, of course, as you expect. And here you have, what is it, 1 million? No, 10 million years. After 10 million years, we get here, and the displacement has increased. Well, it had increased, not so much, but significantly nonetheless. That's only 10 million years. We go on, 10 million years. 20 million years. Mm-hmm. 20 million years. And the increase has become greater, and so on. It becomes greater the further you go back into the past. Okay, I will zoom out now, because these numbers, you can do these calculations yourself. If you don't trust my calculations, you can do this yourself. Here, half a billion, you know, what is it? 50 million years. Well, let's go to 1 billion. 1 billion years. Well, after 1 billion years you got, is this 1 billion? 1, 2, 3, 1, 2, 3. No, 100 million, sorry. Let's go to 1 billion. Half a billion. So now the displacement is going to 4.25 centimeters. Half a billion years. Well, let's go to 1 billion. Here we are, 1 billion. It is now at least 1 centimeter more than where we started with. We started with 3.82 centimeters. After 1 billion years, this is the increment of the displacement of the Moon has 1 centimeter bigger than where we started. And you say, well, that's not too much. That's right. For this moment, it's not too much. But the thing is, this is itself enforcing process. Now we go to, let's go to 1.5 billion years, so 1.5 billion years. Okay, that's this one. Now you see here an annual displacement of 5.6 centimeters. So 5.67 centimeters per year. The displacement in those days, supposedly that these days have existed, which I don't believe. That's what I'm trying to make clear to you. 1.5 billion years ago, the displacement was much bigger because the Moon and the Earth are closer, so the forces are higher. As the forces are higher, then more heat is generated, more energy loss is generated. So the displacement must have been bigger. The rate at which the Moon would leave the Earth would have been bigger. It must have been, because the tidal forces create internal friction in both planets, and due to heat loss, you lose a bigger amount of heat if the two objects are closer together, because the forces are bigger. Simple. You don't need to be a rocket scientist for that. Okay, after 2 billion years, let's go to 2 billion years. I have take a bigger increment of years. 2 billion years here. As you can see, the moon has very much closened to the Earth. The distance between the Earth and the moon is now only, what is it? This is in meters, so it's only 284. What is it? This is meters, so this is kilometer. 284 kilometers, which is 100,000 kilometers closer to Earth. Only 2 billion years ago. And the increment, let's see, that's this one. The annual increment has risen to approximately 7 centimeters per year. So what you see is basically an increment, an increasing increment. So an acceleration, or because if you go back in time, it's an acceleration. If you go up to our time, it's deceleration, of course. The increments of the annual displacement of the moon is reducing the further you go in time. Okay, let's go to 2.5, 2.5 billion years. That's this one. Now it's 9.5 centimeter of displacement, annual displacement. What you also will notice, is that the energy released, the power, which is this, the displacement times the energy released per centimeter, is also increasing. And thus the power, the watts per second, or the joules per second, which is watts, is also increased on the total surface of the Earth, the planet Earth, and the moon. This is only after 2.5 billion years. I'll go to 3 billion years, to 275, but let's say 275, because you are going faster and faster. This process is going faster and faster. Now you are at about 12 centimeters of increment per year, and the distance between the Earth and the moon has reduced to what is it? 21. Well, rounded off, 22. 220 to 217,000 kilometers. Go to 300 million, 3 billion years. And here again, the moon has lost another 100,000 kilometers of distance after 3 billion years. The annual displacement has increased to about 17 centimeters per year. And the energy release, the energy loss, has also increased. And now it's getting interesting. I'll do it by 3 billion and 100,000 billion, 3.1 billion years. I'll reduce this. It has increased to 21 centimeters, annual centimeters, 1.3 actually. At 3.2 billion years, it has increased to 29 centimeters per year. And the energy loss is this. By the way, here I have put the ratio between the energy, the watts, and the watts in the beginning when we started. And now the release of energy is 60 times more than we started with. Well, now it's getting interesting because I know where it ends. You don't yet, but I do. Here at 3.3 billion years, supposed years, the increment has risen to about 60 centimeters per year. Let's go slower. Let's put this one. After 3.335 billion years, the annual increment has turned to be 112 centimeters. The energy release is now 870 times higher than in the beginning, than today, actually. 3.35 billion years ago, the increment is 2.5 meters per year. And the energy release is 4,280 times more than we experience now. So the Earth heat, the Earth, due to this force and due to the release of energy, the amount of heat is generated is 4,800 times bigger than it is today. Well, if you know that I found, of course, I looked it up. If you know that the average, what was it? Sorry, yeah. The annual heat release of Earth heat, Earth warmth, is today, on average, it's 91.6 or 7, I forgot, milliwatts per square meter. Now, if you realize that, what is it? 3.35 billion years ago, it was 4,280 times stronger, more heat release. And it gets only worse. I mean, if the planets come by closer, now the moon, in this period of time, the moon is only 47,500, so a little less than 50,000 kilometers away. And it gets worse. And now I made the increments smaller because I know that it's getting closer to a disastrous rate of change. So let's take this one. Now the moon is only, because it's an accelerated, if you go back in the past, it's going faster and faster and faster. Now the moon is only 14.4 thousand kilometers away. The annual increment is 2,700 centimeters, which is in meters 27 meters per year. The heat release, the energy release, is 3.83 times 10 to the 24th in joules, total of joules per year, which is an annual release of 1.2 times 10 to the 17th power, which is, if you calculate it per square meter, is 500,000 times higher than today's 91.7 milliwatts per square meter. So the ground under our feet would be hot, well, very hot. And then finally, where is it? Finally, the Earth and the Moon are so close together that it's impossible. Here you are. Oh, by the way, this is at this stage. I will zoom out where the red band is. We have approached the Roche limit, in which the Moon or the Earth or both break up due to tidal forces. So at this stage, the Roche limit is met. Roche limit, Roche. And if we go further down, here you see displacement. These are displacements, this one, of 9,000 centimeters or 90 meters. And it gets even worse, of course, the closer the Moon gets, the further back in time, and the closer the Moon gets. In the end, the Earth and the Moon, if the Moon would not, let's suppose that we discard of the Roche limit, and we say, okay, we have a very strong Moon. The Moon is entirely made of diamonds, let's suppose, and it's so strong you cannot break it so easily. So the Moon will not break up at the Roche limit. Suppose it would, of course. So actually, based on this, actually, the limit of the age of the Moon is, if you look at here, and that's reality, is, well, this is 3.357 and something billion years old. So the time that what science says that the Moon is 4.5 billion years old next to the Earth is not true. And this is just very. This is not. You don't need to be a rocket scientist to make these calculations. And if we go further back in time, and for the moment, let's discard of the Roche limits, which of course you cannot discard, but okay, let's assume. And I made the increments smaller and smaller, because here, this is the last thing which is possible if you discard of the Roche limit. Now, the increment has gone up to these numbers, which is, what is it, so many centimeters, that is centimeters, centimeters, meters, kilometers, 234 kilometers annually. And if you do that, then you end up negative, so the Earth and the Moon would bounce. They would, the Moon would fall on the Earth. So, and that's at this limit. That's here. So 3.3572858 years, annual years, actually. Yeah. So that's the maximum age that the Moon, according to this calculation, which is not too difficult to calculate, can become. So let's do that. Let's put that in scientific notation. Okay, that is, let's zoom in. 3.35724 times 10 to the power of 9 years old. That's the maximum, according to this calculation, what the Moon and Earth system can be. That is not, as science claims to be, 4.5 something billion years. So I put several things into a graph, which makes it more easy to see. Then we go all back way up to the top. Here it is. Now you can see here, first place I like to zoom in on this one. You can see the increasing increments. If you go back, this is today, and if you go back in time, then the Moon would get closer, quicker, closer and closer, closer. Of course, suppose that the billion-year hypothesis is true, then the increments in the beginning would be very big and slow down to asymptotically to where we are now. And I limited this graph to 500 centimeters because it go way up there, way up off scale. So I limited my graph to 500 centimeters, which is 5 meters. But we saw already that it's much more. It's even about it can be many more kilometers per year. But I left it to 500 centimeters per year. If you put the distance, the Earth-Moon distance due to tidal energy loss in meters, and you would have a graph like this. So this is the actual distance between the Earth and the Moon based on this calculation. I will make it a little bit thicker so that you can see much better. Yep. Now, let's make it a real thick line so you can clearly see it. Well, based on the calculations that I made, which is very simple, and now I can explain it once more if you really don't understand it. But the Earth-Moon distance due to tidal energy loss in meters, and you get to a point where it's closely below 3.5 billion years that the Earth system is supposedly, according to secular science, which I don't believe, old. This is where we are today. Here, this number, this point on the graph. And as you can see that the Moon has, if this whole billion-year story is true, then the increments in distance would be increasing very strongly in the beginning and is slowing down now, asymptotically. And all I did, again, I'll show you. Maybe I repeat myself too much, but okay. Just to be clear, is I took in the beginning an increment of 10,000 years times the present day increment in centimeters per year, and calculated back calculated it what it would mean in distance 10,000 years ago, then calculate the force, which is this one. I'll enlarge it a little bit. So I took this increment per year, which is measured, this is a measured fact, this is a measured fact, and the distance of the moon right now, that's this one, so this and this. I did the increment per year, I calculated it times 10,000, suppose that let's do in steps of 10,000, then back calculated the distance 10,000 years ago, and the force, and the work per centimeters, and based on that I calculated a factor relatively to today, this, and based on that I made recalculated the new increment, or the past increment, which must be bigger because the energy loss is bigger, and if you lose more energy, the more the system will lose distance. And I did that over and over again for 20,000 years, 30,000 years, and so on, so on, so on. So if you don't believe me, you can do this calculation yourself. But it shows that the Moon-Earth system cannot be older than 3.3 or 3.4 billion years old, and most probably it's even less, because I might not take into account all other kinds of energy losses that I did not take into account in this situation, in the Earth-Moon system. This is only based on distance and gravitational and loss due to tidal forces. So the Earth-Moon system cannot be 4.5 billion years old, as the secular science once tries to say. And this is also a problem for evolution, because evolution, the secular science tells us that life, the development of life, started 4 billion years ago. Well, that's not possible. It's not possible because the forces that the moon would put on the Earth were way too big, and the energy released due to that would be very, very big. I mean, the whole Earth would be super hot, only due to the tidal forces. Next to the fact that if the moon is closer and the forces are higher, here this is the watts. This is the watt. So the energy per second, the joules per second over the entire Earth. And in another sheet, I think, was it this one or this one? Oh, here, yeah, here. I got some more stuff. Yeah, this is the. He got it. It's 91.6 actually. That's what I calculated here in another sheet. 91.6 milliwatts per square meter. That is this number. This 9.16 times 10 to the minus 2 watts per meter. I mean, it's 91.6 milliwatts, so it's 9.16 times 10 to the minus 2 watts per meter. And then I calculated the ratio between the two, the development of the ratio in time. And if you look back in time, in the number that I calculated here, where the Earth and the Moon is getting closer and closer. I mean, here, this is, what is it? This is 24 kilometers high, 30 kilometers, 51 kilometers, 65 kilometers, 110 kilometers that the Moon, you can in these situations, you can almost touch the Moon. And here's 24 kilometers, so you can, this is 15 kilometers. So in these cases, the energy release, and if you compare that to the nowadays energy release, it's thousands and thousands of times higher in those days than it is now. So if you were standing here on the surface of the Earth, if you compare this, then you would be cooking on the spot. That much energy would be released by the Earth, only due to tidal forces. So it would be impossible for life to develop. This is craziness. Let me see. It's really craziness. Here it's about 123 times more, which is 3.3 billion years ago. And according to these calculations, which are not so difficult, it's only Newton's law, gravitational law applied, and the energy release due to that, and so on, so on, so on. It's very basic type of calculations which everybody can do. And I'm sure that I left out some other energy losses which make it even worse for this model, and even worse for evolutionistic people, because if more energy is released in the Earth-Moon system, then only this age becomes smaller and smaller. This is what I wanted to share, but now calculative wise, to show you that the Earth cannot be as old as secular science wants you to believe. It's impossible, and that's a problem for evolutionistic ways of thinking, and it's a problem for people who believe that life has emerged from chemicals from the sea, and that we all started off like fishes and bacteria. We didn't. And this is just one way of showing it. Okay? Well, thanks for watching. It's been a kind of pretty much work, but I like to present it to you and to show you again and again and again that science is not on the hand of evolutionistic or billion years type of people, but is really on the hand of biblical timescales, and not on evolutionistic timescales, not in billion and million of year timescales. Okay, thank you for watching, and see you next time. Hasta la vista. Bye bye.